But what I've been looking at is how bedrock rivers are transporting coarse sediment. And I'm looking at a series of rivers across Taiwan. And one of the things that you can see in these drone videos is that the rivers are incredibly variable. So we have these incredibly coarse sediment. This is up to 10 meters in diameter. And actually, I'm going to come on screen in a moment for scale. Oh, there I am. And so you can see that there's spatial patterns in the grain size. We also have patterns in where it is relative to the banks and patterns relative to bedrock exposure as we move down these different rivers. And so one of the things that we're interested in is how these bedrock rivers are transporting sediment and eroding the banks and eroding into the bedrock. And we need to look across the full range of variability and understand how is this changing over space and also how is this changing over time. So what are the variability in the spatial locations of sediment transport capacity? And also how is this changing with different flows, different flow events? So the way that we're approaching this is with a series of drone surveys. So on the left is the drone survey from the field, and on the right is the photorealistic 3D model that we can actually make of the exact same site. So these are not quite exactly aligned, but you can see that these are highly photorealistic. They're representing the full 3D geometry of the channel. We're able to pull out the full grain size distribution and actually see what's going on here. We can then go through these different river systems. This is an animation of another 3D model. And we can move up and downstream throughout these channels and map just like we were in the field. We can actually pull out things that are more difficult to map in the field. This is actually one that we've had to survey from a trail. It's not possible to get down into this bank. But we can go through and we can map lithology like we would in the field. We can pull out full grain size distributions, measuring every single grain that is in the channel. We can pull out things that would be really difficult to measure in the field, like the high water marks that we're seeing in the channel, breaks in that vegetation or that weathered bedrock. And we can also pull out where that current water is. And then we can see how this changes at different points in the channel. So this is an example of the kind of data density that we can get out of this. So this is a 1 kilometer reach in northeastern Taiwan. And basically we have measurements of the bed slope across the entire channel, the high water marks, the channel width at both high water and low flows. We can also measure the relative area of sediment, both coarse sediment and fine sediment. In Taiwan, fine sediment is like less than a meter, so different than other systems. We can measure the distribution of boulders throughout the system. And what we're actually starting to see here is that the spatial variability in these rivers is actually pretty much due to the rock strength. So we have variations in the lithology of bedrock that is exposed at the surface, and that is changing where you're getting wide rivers, changing the channel morphology. So here, for example, the black schist, our relatively weakest rock, is creating much wider river channels. And that river channel, it's actually widening when we are parallel to the foliation angle of the bedrock itself. So you have structural variability that is really creating the spatial variability in the system, and that's actually corresponding to where we're getting different sedimentation patterns. So cool to see it change over space, but we can also measure it over time. So these are photorealistic surveys that have full 3D capability. And so we can take a series of repeat surveys. This is further downstream of the same river where we have 4 repeat surveys. And we can actually compare them and see how these rivers change with different storm events. So we have a really unique data set. This is about a 200-meter reach also in northeastern Taiwan, where we have a range of grain sizes anywhere from kind of 12-meter boulders down to kind of fine sand. And these different surveys capture a range of different discharge events. So between 2015 and 2017, we actually captured a typhoon. Between 2017 and 2018, we had a high flow year, not a typhoon, but still high flow. And then between 2018 and 2019, there were relatively little storms. So we can start to compare this kind of data. So we can fully map across these reaches the different distributions of different grain sizes. So this is between 2015 and 2017, that change where we're capturing the typhoon event. And we can actually measure the differences in the grain size distribution throughout. So overall here, we're not seeing a large change in the overall grain size distribution, but we are seeing a lot of change in 3D. So we can actually measure aggradation and erosion at really high resolution. And we're seeing up to a meter of aggradation and a meter of erosion throughout this system, and it's non-spatially uniform. We can actually go through and measure every single boulder that was in this channel and see whether it moved or not. So about half of the boulders in this system did move in this time period. And while it is more likely for the finer grains, the 1 meter boulders to move, we are seeing up to an 8 meter boulder moving between these two surveys. If we move in from the typhoon year to the stormy year, we have less overall change. We're seeing a net erosion throughout the system. We're transporting fewer boulders, but we're still transporting up to a 5 meter boulder in between that time. But we're seeing a really big change in the grain size distribution that we're actually seeing in the channel. So all of a sudden, we've lost a lot of our gravel, and we're increasing all of our other size classes. So we're actually making the channel more complex, and we're reorganizing the channel and getting a lot more of a rougher surface that we're seeing there. And this is kind of, that gravel is eroding out in these patches all throughout the system. Between 2018 and 2019, where we have a relatively quiet year, we don't see much change in the overall bed state, but we still see more of that gravel going away and the other size classes increasing. And so this kind of spatial pattern is showing that it's incredibly complex to move these kind of flows with this wide range of grain sizes, but we can start to capture the full complexity both in the surface measurements and in the actual full grain size distributions. So overall, this has shown that we can use these kind of surveys to measure things over both space and over time and see how the different sediment is able to be transported differently wherever we are in the stream. And we can use these repeat surveys to see how it'll change over time. So thank you for having me here. I'm done.